Hey everyone. Okay. I want to get you on to this activity where you're going to actually identify some characteristics about exoplanets. And basically, all you're going to be determining is how big they are, how far away they are from their planet. But it's amazing how you're going to come about this because you're going to use it with very little data and almost no math. The math you're going to use is very straightforward, and I'll walk you through it. It is necessary to do this math because there's no other way to figure out the size of the planet, and it's going to be kind of interesting what you come up with. So let me get you started. First of all, we just watched the video that talked about how they found exoplanets early on, and they used something that I don't think they actually termed it this in the video, but it's known as radial velocity. So, radial velocity is basically just looking at the spectrum of a star and watching it shift from red to blue, meaning it's wobbling, and trying to determine if that wobble is caused by an exoplanet. And it'd be a very tiny one. And while that was effective for finding some extremely large planets that were very, very close to their stars, it doesn't really work for smaller planets, and especially if those planets are farther away from their star, having less effect on the wobble of the star. So, so what we're going to do though is look at the most what's called prolific, what produced the most results for finding exoplanets, and that is basically a satellite that was called Kepler. And if you remember Kepler from way back in the first semester, he's the first scientist to ever come up with three laws of nature, with any laws of nature, and he came up with three. One is that the planets are in uh, elliptical orbits, and two was that you can determine how far away those planets are based on how long their period is or how long it takes them to orbit their star. And we're going to use that. You'll be able to tell what the orbital period, how long it takes a planet to orbit its star, and based on that, you'll be able to find how far away it is from its star. There is no math involved in that. The math has already been done for you. You're going to use another method that shouldn't be too difficult. My main reason for doing this is not to create a math class. It's just to show you how scientists use data and how what they know is actually extremely valid based on the data that they get. And so I just want you to kind of become familiar with that. Okay, so the transit method is what we're talking about here. This is when a planet goes between the star and the Earth, us way over here. You know, it has to go in between the star and the Earth if it's going to block any of the star's light so that we can tell uh, all of this data about it. Now, if the orbit of the planet is around the star in such a way, like, say, holding a frisbee sideways and throwing it straight up in the air, you know, thinking about that and it's spinning, uh, we're not going to see any light lost by the star from that because the planet will never come in between the Earth and the star. So this only works for those stars that have planets that go in between us during their orbits. And it's turned out to be very good. We had this satellite called Kepler, and it did what's called a survey of the sky for 50,000 stars. I'm sorry, 50,000 stars. And it would do this survey, basically look at them and take measurements very quickly. In a matter of hours, it could do it. And it would just do it over and over again and collected tons and tons of data on these stars. And the scientists were able to take that data, and they're still doing it. There was so much was produced over the years that they are still accessing the data and working with it, that they were able to produce what's called light curves. And I'll get to what light curves are here in just a second, because that's what you're going to be using is light curves. So in order to understand what these are, we need to understand a little bit of things. There's three big challenges in trying to observe exoplanets. They are very, very far away. They are light years away. They are tens, hundreds of light years away, and they are tiny, 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 tiny. So they are hard to see. And what's worse is they don't produce any light of their own. They're just dark rocks. If you have a rock in a room and you turn off the light, you can't see that rock because it produces no light of its own. So that makes them very hard to see. You have to be able to find some other way. We see our planets in our solar system, even with our naked eye, because they reflect light from the sun. They don't produce their own light, they reflect light. Well, exoplanets, if they get to the point where they're reflecting light from the sun that we could see, they'll be behind their star. So, that doesn't work. We can't, there's really very little ways that we can see these tiny little specks orbiting very, very bright stars. So they're an enormous distance from us. They don't produce light of their own, and they are lost in the blinding glare of their parent stars. I mean, these stars are bright. Just imagine looking at the headlights of a car on bright as they can get, and you pass a little piece of hair across the front of it. You're not going to see that hair. There's just too much glare from those lights. And that's the equivalent of what's happening with these stars and the planets going in front of them. So that is the challenge that faces us. Now, with just a few exceptions, we actually do have pictures of exoplanets, not pictures like you would think. We have pictures that show blobs that move around a star that we have blocked the light. We use that pantograph in front of to block the star's glare. And we can see light that's being reflected off of a planet that is so huge, right? A massive planet. And we see that planet move a little bit as we take several different pictures over the years, and that planet moves. We get, okay, that's a planet. We've actually got a picture of that, but that's all we've got. It doesn't tell us anything else about the planet. With a few exceptions of those, we have no pictures of any planets that we found. Anytime you see somebody describe what a planet looks like, an exoplanet looks like, it's from data they deduce, and this is their best guess. And it's an artist that has drawn or painted the planet for us. So just keeping that in mind. And usually the guesses probably are pretty good, but one day we'll probably find out, not us, but somebody will find out what they really, really look like. Okay, so here's kind of what the transit method would look like if we could see it from a bird's eye view really close to the star and the planet, and the star didn't blind us while we were looking at it. But this is an artist rendering of an actual planet, HD 209458. This would be HD 209458b, going across the front of its star. It's transiting. It's going between us and the star. And this is a gas giant. I can tell just by looking at it because it's leaving a huge gas trail behind it. It's so close to its star that the gas is literally being boiled off of the planet. The planet is shrinking as we look at it because the sun is just boiling all that gas off of it. And eventually that gas will leave, and we don't know what will be at the core. If it would be like a rocky planet like the Earth, excuse me, or nothing, or whatever would be there. But that is what you're looking at there, is an artist rendering of what this planet looks like orbiting that close to the sun with all that gas coming off. Now, side note, There is a theory, it's not well accepted, and it's not really pushed out there, and nobody can really know for sure. But what's to say that all of the four planets, Mercury, Venus, Earth, and Mars, aren't the core of some gas giant that was so close to the sun that the gases boiled off over time? The big thing about that is even if you have a planet the size of Jupiter, it would take many billions of years, more years than the Earth has been around and the sun has been around for that to happen. So that's probably not the case, but it's kind of an interesting thought. So, but that's kind of what we're looking at there. So, the transit method is a planet passes directly between the Earth and the star that it's orbiting, and we take a reading of how much the intensity of the light coming from that star drops. And because the planets are usually very small compared to the star, it's not much of a drop at all. It's tenths of a percent of the light, hundredths of a percent. But Kepler's instruments and the instruments of other satellites and other telescopes and things that we have actually are sensitive enough to see that difference. All right, and so that's really something amazing about our technology is we can we can see such a small drop in a star's intensity. Now, it's not necessarily a proven fact every time you see a star's intensity drop. That's because of a planet going in front of it. It could be many other things going on as well. So lots of different verifications and data gatherings and study has to be done to verify that that was actually an exoplanet. The McDonald Observatory in West Texas was one of the key players in verifying exoplanet discoveries. They would be the ones to go out and they would take the data that scientists gave them and say, okay, yep, we verified this is an exoplanet, or no, this was caused by some other thing going on with that star, which could be just as interesting, but it wasn't an exoplanet. So that is basically how that works. Now, what you're going to see when you have an exoplanet go in front of its star, between us and the star, is a weird looking what's called a light curve. You have the base intensity of the star. This is how bright the star is, right? And then as the planet starts to go in front of it, that intensity drops, right? Because it's blocking some of the light. Now, this is not saying it's going to block half the light of the star. This is just where they drew the line. But it's going to drop until it reaches, it's completely in front of the star, and it's going to flatten out down here at the bottom. Okay, it's because it's not blocking any more light. That's all the light it's going to block. So it blocks it, and it blocks it for as long as it's going in front of that star. All right. And when it gets over here where we could have put position 4, you'll see just the reverse happening because it's going away. It's blocking less and less and less light until it's completely passed. And then you're back to the normal brightness of the star. Right. So that's a very telltale sign, a very good clue that the dimness coming from the star, the dimming value of it, is caused by an exoplanet. Other things that cause them to dim don't have a nice pattern like this for the most part. So there's how they look at it. All right, so when you see a curve like that, you can tell some things right away. Number one, how often it happens will tell you the period or how long it takes that planet to orbit the star, because you'll have this drop. Let me go back. You'll have this drop, and then the planet orbits around the star, goes around behind it, and then comes back to the front, and then you'll see this again. And how long it took to go from this one to the next one tells you how long it takes to orbit its star. So that's number one thing that you can get from that. Number two thing is you can deduce the size of the star and the planet from these things. One of the you kind of need to know the size of one of them to tell the size of the other, but there are ways of doing that. But here's how you can look at this. Here we got stars that are different sizes, right? We got a big one, medium one, small one, and we got a same size planet going across both of them. All right, these dots are the same size. As they go across, the longer it takes for them to go across, the longer this bottom line is going to be. Right? Because that's just the way it is. When it's not very big planet like C here, it's not going to take very long for it to get across. So this is not going to be very long. However, it's going to block a whole lot more of that light, a bigger percentage of the light of that star than it does for the big one. So if you see a small dip, but it takes a long time, then you got a big star with a small planet. All right, a big dip in the light, but a small time to get across. The planet is very big compared to the star, right? So there's some data points that you can actually start deducing some information. And here we go the opposite. We have a star that's the same size, but different size planets going across it, and kind of the same thing. The bigger the planet is, the more light it's going to block, so it'll make a bigger dip. But the shorter time it will take to get across and start going back up because it's bigger, so it covers less area compared to its size than the small one does. It takes the smaller one much longer to get across than it does a big one. Think about it. You got an ant crossing your floor, and even if it walks in a straight line, say, I don't know, in your kitchen, even if it's walking in a straight line, it's going to take longer to get from one wall to another than it would take your cat to get from one wall to another, or from you to get from one wall to another, because you're bigger, right? And so that's how we can tell we've got a relative size difference between the star and the planet. And then you're going to use this. You're going to use all of these things to your benefit. Okay, so let's get looking at what you're going to be assigned. You're going to be given several, and they're available in Schoology. They're the next thing you click on below this. It's going to be a worksheet, and you're going to basically answer some questions. Now, it's going to ask you to fill in a table. What I want you to do is just create a Google Doc. If you can build a table, that would be great. If not, just line the numbers that you put in there up with what would be in the table that you see in the document you download. Okay, because I don't think you'll be able to enter. Let me think about that. Okay, you may be able to. You may be able to. I can't remember if I made it a Google Doc or if it's a PDF. If it's a Google Doc, you'll be able to enter it and just fill in the tables, and that'll be great. If not, just create your own way of answering and filling those in and answering on a separate sheet of paper. But hopefully, I was able to make these into a PDF. A lot of times, PDF doesn't like these kind of figures and things, so they really mess up the formatting. So hopefully we'll see how it works. But okay, all right, so here's what we're looking at. We're looking at these graphs. Do not ever measure from, say, here at the far left edge over to the first one, because you don't know where they started measuring this. Always measure from the first one to the second one dip. These are the dips. This is where the light is for the star normally. Not a perfectly straight line. It's okay. This is just part of data gathering. There is fluctuation. It's not really significant though. And then you have the dip. All right. You got the star that went across it, and then it was done. Now this looks to me like it's a big planet compared to the star, because it didn't take very long, but it really dipped a long way down. it dipped down. It took 0.16% of the intensity away from that star, which doesn't sound like much. 0.16, less than 1%, 6.16. I can't even think. It's less than 1%, way less, almost 0%, but it's 0.16%. Doesn't sound like a lot, but that is a lot for a star to be blocked. All right. And you can count how many days it took it to go from the first blockage to the second blockage, transit, I should say. And in this case, it goes from day 3 to day 6. So it's 1, 2, 3, but it was a little bit before day 3. So I'd say, and a little tiny bit after day 6. So I'd say 3.2. 3 days, 1, 2, 3, plus these extra little bits here, I would put out there about 3.2. So 3.2, the period of this planet going around the star, the time it takes to go around the star is 3.2 days. All right. So what you do with that is you'll have a sheet like this. And this is the one I'm not sure if you can fill this in or not, or if you have to just create another one. You have a sheet like this, and whatever that is titled, this one didn't have a title on it, so I don't remember which one it is, but we'll say it's Kepler 4b. You put in 3.2 days for the period. All right. Now you'll do that for each one of these. Once you have this filled up, you'll look at all those charts and immediately go in there and cross off one of these mystery planets. It doesn't matter which one. You only have one mystery planet in the thing with no name on it that you're going to try to figure out. All right. But so one of these you just cross out, one of the mysteries. All right. Once you have all these filled in, the way you're going to figure out what the orbital distance is very straightforward. On the next page, you'll have some graphs. All right. Most of your periods will be less than 10 days. So this is the graph for periods of less than 10 days. Here's the period. And it will tell you the distance because of Kepler. Kepler was able to figure this all out, give us the mathematical formula, so we can just create a nice graph like this. And the one we were just looking at was 3.2 days. So you come up here, 3.2 days somewhere along here. 1, 2, say up here. You come across here, it's a little bit past 6 million, 2 or 300,000 kilometers. All right, because this is in millions. So that's 6 million, 7 million, 8 million. So that's how far away that star. That's not very far from its star at all. But that's where that exoplanet is. So you do that for each one of these. Now, if you have one that is like 20 days, well, then you come up here and use this one that's for less than 100 days. And if you have one that's listed in years, so be sure you look down here and make sure that's time in days or time in years. All right, and those are Earth days and Earth years. To know which one of these that you use. So anything less 3 days or less, use over here. I'm sorry, anything 10 days or less, use over here. If it's 100 days or less, use over here. And you don't want to use, because, up here to 10, it's not very accurate. I mean, you can't really tone it down, but, just use those as best you can. All right, just find what you need to and put them in there. And so then you put in your orbital distance, and you see how far away they are from their stars. Now, this is a little more involved, a little bit more math, but not too bad. When you look at this, the percent of the star brightness that is blocked is 0.16. All right, it's actually a little bit more, but I don't even think, I'd just go with 0.16 on that one. You put 0.16, 0.16. That's all you do. And you put that down here for all of these. Then over here, you take the square root of that, square root of 0.16. And you write down for every one of these that you got, you write down again, cross off one of the mysteries. You cross off, you take the square root, and you just do that in your calculator, square root of 0.16, and write down the number that goes in there. You don't need to go more than 2 decimal places, okay? And then you take this number over here and you just multiply it by 10. That's all you do. So you write down the 0.16, take the square root of it, multiply it by 10. And this 10 tells you how many Earth radii that it is. That is basically, we're comparing it to the size of the Earth. So if it's less than 1, if it's 0.5, say, then it's probably about half the size of the Earth. If it's like 11, then it's 11 times the size of the Earth. And that's all you're looking for is the size of the Earth. All right. So, and then at the end, you have these 3 questions based on what you see here and see here and what you see here. All right. So for my Orange Day, I am here to help answer questions. For my White Day, I am not here to help you guys out with questions, but hopefully if you listen to this carefully and look this over, you should be able to do this quite readily. I won't say easily. It should be easy, but it's the first time you're looking at it and you may struggle with trying to understand what to do. Just take it off. Don't try to do the whole thing at once. Just do each one of these columns. Just do what they say here. Find the period. Use the graph to find the orbital distance. Write down what the brightness is. That's basically brightness drop is 0.16, might be 0.08, might be 1.1, who knows? And then take the square root and then multiply that number that you get in this column by 10, and that's the answer that you want. That tells you how much its size compares to Earth. And that's all there is to it. And that's all from reading this one little thing here. All right. So there you have it. There's the transit method. When we come for next block, we're going to do this for real data. We're not going to find orbital distance or any of that stuff. We're just going to look at data and verify whether it's an exoplanet or not from real data. So that's something I think to look forward to, and good luck with that. If you struggle with this too much, email me. I will try to help you out. I should be available most of the day by email. If I'm not here, if you're my White Day. All right. Thanks a lot. That's it. Good luck with the exercise. And I am scoring this as a lab because I think it's lab worthy. And I really hope you understand that really what I'm trying to get across here is just how much you can know about something from just a little bit of data that's gathered by it. And that's how scientists do all this stuff. All right. We'll talk to you next time.